Okay, welcome everybody. This talk is about quarks and the search for elementary particles. Basically, people have, as long as there have been people, we have always thought about what matter is made of, and there was always a search for the basic elements of where everything was built out of. Although the first idea wasn't the four elements like earth, water, fire, and air. Basically, thousands of years before that, we already knew of 9 chemical elements. We find them in all kinds of materials. These elements, as you can see here, so carbon, in the familiar system that you know, carbon, sulfur, iron, copper, this is silver, this is tin, I think, gold, mercury, and lead. They were already known. We see them in all kinds of stuff, and they have been known already. So those are 9 chemical elements, as you know. Later they found 5 more. Basically, we find them in several instruments and stuff like that. And well, from 1669 on, there was a proper search for more elements, and basically then it really took off, and it looks like this, the graph. So we started 14 here, these 14, and then basically it increases, and basically this is almost linear progression. So this name should mean something to you. Mendeleev, he thought of the periodic table, of course, and there were already 66. We're now at 118, 94 of which are stable elements we find in nature, and 24 of them are, as we call, synthetic. They are made in the lab, and they are unstable, so that means they only exist for a very short time. We can discover some properties, but you won't find them in nature. But basically they are elements, and there's no reason that it would stop anytime soon. So this might continue some bit, so we don't know where it stops. And there's even talk about there being an island of stability just ahead. So perhaps there are more elements a bit further. But basically the whole periodic system looks like this, periodic table, and there is an organization to it, but as you can tell, if there are 118 basic elements to matter, that's still a huge amount of different elements, and perhaps that's true, but the search for smaller particles was on. Basically, they were thinking about if these atomic, these chemical elements, they consisted of some basic elements. So they were looking for the indivisible part, the basic element of matter, and indivisible in Greek is atomos, and basically the atom is the indivisible part, the basic element of matter. And they were looking for that. Now this name is funny if you know what's coming, but okay, you will see that. The ancient Greeks also knew that in amber, that's something like this. You can have it in a piece of jewelry or whatever. If you rub it against a fleece, then it attracts little objects. So there was a sort of attractive force then, not when you don't rub it, but if you rub it, you get an attractive force. And the Greek name for amber is electron. So of course we know the word electron because of electric charge and everything, and that's where it comes from. Then in the 19th century there was, or 18th century already, there was research into electricity. They thought electricity is a sort of fluid with a positive and a negative fluid, and it's not a very strange idea, but basically in the 19th century the research into electricity took off, and they started doing research with cathode rays. Now a cathode ray is basically a tube, a vacuum tube, so an empty tube with a cathode, that's a negatively charged electrode, and an anode, positively charged, and then you apply a large potential, so a large voltage potential over these electrodes, and then the current will start to flow in the vacuum. And basically, if you look at the current and it hits the glass behind the anode, it looks like this. You get a green glow, and you can also, if you put an object in between, you can throw a shadow, so you can stop the electric current from going there. But there's more happening, because if you do experiments with that cathode ray, then you can see that if you hit it in a paddle wheel, the paddle wheel starts to turn. So basically that means that there are, well, some massive things hitting it, and that makes it turn. And you can also use magnetic fields and deflect the beam. And later on they also found that with electric fields you can also deflect it. So basically it tells you that there are electrically charged or negatively charged particles in the cathode rays. And they did this experiment, and they looked at how much the deflection is, and from that they found the mass-charge ratio. It is almost 1/2000th of a hydrogen ion. That means that these particles might have the same mass as a hydrogen particle, but a charge that is almost 2,000 times as much, or they have the same charge, but a mass that is almost 2,000 times less. So they measured the heat generated, and they found that the heat generated corresponds to particles that are very light. And then basically they found the electron with that, so discovery of the electron. And this is the actual instrument that they use. It's this big, and it's very nice. It's a glass tube, and there's electric coils here to deflect the beam. And if there would have been green light, the green light would have been here, the fluorescent light stuff. So they found the electron, the first subatomic particle, very light, only a tiny fraction of the mass of the atom, and negatively charged. So the atom, the indivisible part of matter, was basically cut into two parts, well, a very tiny chip and the rest.